Continuing on physical chemistry, chapter 9, we're going to do section 6 now. We're going to talk about the thermodynamic properties of ideal solutions. Now remember, this is a hypothetical model, just like an ideal gas. So first of all, we need to define what are the standard states for solutions. Now, there are three different types of solutions: gas, liquid, and solid. So for gas, we say that it's in the standard state if it's pure, and it's an ideal gas. The pressure is called P0, which is 1 bar, and the temperature is whatever temperature of interest we have. Now likewise for liquid solutions, the standard state is the pure liquid, that is before it's mixed, obviously. The pressure is the pressure of the solution. SOLN is the abbreviation we're going to use for solution for now. And then the temperature, of course, is the temperature of the solution. So notice capital P subscript SOLN, that's the pressure of the solution. And then capital T, temperature subscript SOLN for solution. Likewise, for a solid solution, for the standard state, we're going to say it's the pure solid. And again, we're going to have the temperature of the solution and the pressure of the solution. Now let's look some more at our nomenclature. So remember, mu is our chemical potential. The subscript I means our substance I, and then naught means in the standard state. So mu subscript I superscript naught is the chemical potential of substance I in its standard state. Now remember, star, this is the pure substance. So we have this mu subscript I superscript star. So that's the chemical potential of the pure substance I. Now remember, mu I sub naught, or superscript naught, is defined as the chemical potential of the substance in its pure state at whatever temperature and pressure of interest we have. Now that's the standard state. Now just the chemical potential of I, we're going to say that's the chemical potential of I, pure, plus the gas constant R times the absolute temperature times the natural log of chi sub I. Remember, chi is the mole fraction of the substance I in the solution. Now, 1 and 2 are the definition of a solution, of an ideal solution. Okay, I see what I did. So this 1 up here and then the 2 down here. So these two together, the definition of the chemical potential in the standard state and then this change, these are both true if you have an ideal solution. Okay, so now we talked about standard states. What about mixing quantities? So the change in the Gibbs free energy from mixing is going to be equal to the Gibbs free energy of the substance I minus the Gibbs free energy of the substance I in its pure state. Remember, the superscript star means in the pure state, the pure substance. Now, this is supposed to be a G. So the change in Gibbs energy from mixing then is going to be the sum over the amount of all the substances N, or I, substances I, times this change. The molar Gibbs energy of substance I, that's supposed to be an I, minus the molar Gibbs energy of the substance I in the pure state. And this, of course, is assuming constant temperature and pressure. Now the molar Gibbs energy, of course, of substance I, we all know that's just going to be the Gibbs free energy of substance I divided by the number of moles of substance I. The change in the Gibbs energy of mixing is going to be equal to the sum over all the number of moles of each substance I times the chemical potential of substance I minus the chemical potential of the pure substance I. So obviously this over here means in the solution. Now, the chemical potential of substance I minus the chemical potential of the pure substance I then is going to be equal to the gas constant R times the absolute temperature in kelvins times the natural log of chi I. This, remember, is the mole fraction of the substance I. Now the change in the Gibbs energy of mixing is going to be then equal to R times the absolute temperature times the sum, the number of moles of each substance I times the natural log of chi I. But this, remember, of course, is assuming we have an ideal solution at constant temperature and pressure. But it is pressure independent. It'll work at any pressure as long as it's a constant pressure. Now, since chi I, a mole fraction, has got to be greater than 0 and less than 1 for a solution to be relevant, then the natural log of chi I is going to be less than 0, which means that the change in the molar Gibbs energy from mixing has to be less than 0. What that means is that mixing is irreversible or spontaneous, which is kind of obvious. If something is soluble, it's going to mix spontaneously and not undissolve itself. Now the differential of the Gibbs energy is going to be equal to the volume times the differential of pressure minus the entropy times the differential of temperature. Now, we're assuming constant temperature, so that differential term, dt, is going to be equal to 0. So all we end up with is the differential of the Gibbs free energy is going to be equal to volume times the differential of pressure. Now we know that volume is going to be equal to the partial derivative of Gibbs free energy with respect to pressure, holding temperature constant. The change of volume from mixing is going to be equal to the partial derivative of the change in Gibbs free energy from mixing with respect to pressure, holding temperature, and the number of moles of each substance I constant. Now, since the change in Gibbs energy of mixing depends on temperature but not on pressure, then we're going to say the partial derivative of the change in Gibbs free energy from mixing with respect to pressure, holding temperature, and the number of moles of substance I is going to be equal to 0, since it's not pressure dependent. So what that means is the change in volume from mixing is equal to 0 at constant temperature and pressure. That's for an ideal solution, obviously. Now, the change in entropy from mixing is going to be equal to minus the partial derivative of the change in Gibbs free energy from mixing with respect to temperature, holding pressure, and the number of moles of each substance I constant. And that's going to be equal to minus the partial derivative of this whole term with respect to temperature. This term meaning the gas constant R times absolute temperature times the sum over all substances I of the number of moles of each substance I times the natural log of the mole fraction of each substance I. This is a subscript I. And that's holding pressure and the number of moles of each substance I constant, of course. So the change in entropy from mixing is going to be equal to minus R times the sum over all I, substance I, of the number of moles of substance I times the natural log of the mole fraction of substance I, for an ideal solution, of course. And again, since the mole fraction has to be between 0 and 1, then the natural log is less than 0, which means the change in entropy from mixing is greater than 0. Now, that's not always true, though. For example, let's talk about, chloroform and acetone. The change in entropy from mixing is actually less than 0, but the change in Gibbs free energy is actually still less than 0. Another counterexample, so we have dimethylamine and water. The change in entropy from mixing for that is also less than 0. But again, the reason is that's not really an ideal solution. Water is a much smaller molecule than diethylamine. And of course, for an ideal solution, the molecules would have to be about the same size. So that's why that sort of breaks down right there. Now we have the change in Gibbs free energy from mixing is going to be equal to the change in enthalpy from mixing minus temperature times the change in entropy from mixing. So you solve for the change in enthalpy from mixing and you get the change in Gibbs free energy from mixing plus temperature times the change in entropy from mixing. So we substitute in and we get the change in enthalpy from mixing is equal to the gas constant R times temperature times the sum over all the substances I of the number of moles of substance I times the natural log of the mole fraction of I minus R times T times the sum over all the substances I of the number of moles of substance I, natural log of the mole fraction of I. These cancel out, they're the same. So the change in enthalpy from mixing is equal to 0. So for an ideal solution, the change in enthalpy from mixing is 0, which means there's no heat of mixing. The temperature shouldn't change. So let's say we have an ideal solution of substance A and B. So here's a graph showing, okay, if we have pure A over here, pure B over here, half and half in the middle here. So we've got the vertical axes in calories per mole, which is kind of arbitrary. It's just energy per mole. It's intensive. So that throughout anywhere, the change in enthalpy from mixing is 0. But what happens is you add more and more and more, you get your change in until you get about half and half, you've got two terms. The temperature times the change in entropy and the change in Gibbs free energy. So as you get towards about half and half, the entropy term increases, and then as you get beyond half and half, the temperature times the entropy, change in entropy term decreases. Likewise, as you get towards half and half, the change in the Gibbs free energy gets the most negative, and then as you get beyond half and half, then the change in Gibbs free energy is still negative, but it's not as negative. Of course, it's always negative, so it's always spontaneous. It's just what you would expect, that it's the most spontaneous, however you want to say that, at half and half, since the two species are identical. It's an ideal solution. So, since they're sort of a mirror image of each other, I didn't necessarily draw that very well, but basically whenever the temperature times the change in entropy of mixing term is at the maximum, then obviously the change in the Gibbs free energy from mixing is going to be the minimum. So you notice there's the steep slopes at the end. It's not real obvious, but it actually kind of curves way up. So that's why it's actually hard to get something like 99.999% pure, because right there it's actually very difficult. So as an example, even though there's a lot of gold dissolved in the oceans, it's very low concentration. So getting that gold out of the ocean would be very impractical. And the gold in the ocean is not pure gold, it's like oral chloride, however you want to say that. For ideal solutions, the change in the enthalpy of mixing is equal to 0, and the change in volume from mixing is equal to 0. If a solution has a change in enthalpy of mixing to 0 and a change in volume of mixing from 0, though that's not enough to conclude this is an ideal solution, though. You have to go back to our definition. Oops, yeah, that's true. Now let's talk more about the change in enthalpy from mixing. That's equal to the change in internal energy of mixing plus pressure times the change in volume from mixing. And again, we're assuming constant P. So the change of enthalpy from mixing is equal to 0. The change in volume from mixing is equal to 0. So the change in internal energy from mixing is equal to 0 for an ideal solution. Okay, now let's talk about vapor pressure with an ideal solution. Now, we know that the pressure of the substance I is equal to the mole fraction of the substance I times the total pressure for all gases. Now, remember, capital P is the total pressure. V is so the small v we're going to use to represent vapor, and this little cursive L we're going to represent liquid. So the chemical potential of substance I in liquid form is equal to the chemical potential of substance I in the vapor form. This is our condition for a phase equilibrium. So it's the same substance in two different phases, vapor and liquid. So here's a container. We have substance I in the vapor phase, substance 1 in the vapor phase, substance 1 in the liquid phase, substance 2 in the vapor phase, substance 2 in the liquid phase, etc., all the way to substance I in the vapor phase, substance I in the liquid phase. So we have vapor above a liquid, exactly like you would expect. So the pressure is going to be equal to the pressure of substance 1 plus the partial pressure of substance 1 plus the partial pressure of substance 2 plus the partial pressure of substance 3, all the way to the last partial pressure of substance I. So this is called Dalton's law of partial pressures. And again, this assumes ideal gases and that there's no reactions going on. Now for phase equilibrium, the chemical potential of I in the liquid form is equal to the chemical potential I in the vapor form. The chemical potential I in the liquid form is equal to the chemical potential I in the liquid form in the pure state plus RT times the natural log of the mole fraction of the substance I in the liquid form. This is for an ideal solution, of course. Now the chemical potential of I in the vapor form is equal to the chemical potential I in the vapor form in the standard state plus RT times the natural log of the partial pressure substance I divided by the pressure of the standard state. That's P naught, capital P superscript naught. Remember, this is for an ideal gas mixture, and P naught is 1 bar. So this is a dimensionless quantity, so you can take the natural log of it. Now the chemical potential I in the liquid form in the pure state plus the gas constant R times the temperature times the natural log of the mole fraction of the substance I in the liquid form is equal to the chemical potential of I in the vapor form in the standard state plus RT times the natural log the partial pressure of substance I divided by P naught. So what we did was we set these two equal together because they are equal to each other for phase equilibrium. So we're going to call this equation 1 so we can refer back to it later on. So we have the pressure, partial pressure of substance I in its pure state. This is the vapor pressure of this pure liquid at temperature T. Now we also have the chemical potential of substance I in the liquid form in the pure state, and that depends on T and also on the partial pressure of the substance I in its pure state. Now the chemical potential of I, substance I, in the liquid form in the pure state is a function of the temperature and the pressure, partial pressure of I in the pure state. And that's equal to the chemical potential of I in the vapor form, unmixed, star is unmixed, sorry. And that's the function of temperature and pressure of the substance I unmixed. Now we have the chemical potential of the substance I in the liquid form in its pure, unmixed, and that's a function of temperature and the partial pressure of the substance I unmixed, and that's equal to the chemical potential I in the vapor form unmixed, which is a function of temperature, plus the gas constant R times temperature times the natural log of the partial pressure of the substance I unmixed divided by the standard pressure. We're going to call this equation 2. Now we're going to reverse equations 1 and 2 by multiplying by -1. So we're going to get negative the chemical potential of I in the liquid form unmixed minus the gas constant R times the temperature times the natural log of the mole fraction of I in the liquid form, and that's equal to minus the chemical potential I in the vapor form in the standard state minus RT times the natural log of the partial pressure of I divided by the pressure of the standard state, 1 bar. So let's add equations 1 and 2, and what we're going to do is get the chemical potential of the substance I in the liquid form unmixed as a function of temperature and the pressure of the substance I unmixed minus the chemical potential of I in the liquid form unmixed minus R times T times the natural log of the mole fraction of the substance I in the liquid form, and that's equal to the chemical potential I in the vapor form in the standard state as a function of temperature plus gas constant R times temperature times the natural log of the partial pressure of the substance I unmixed divided by the pressure in the standard state minus the chemical potential of the substance I in the vapor form in the standard state minus the gas constant R times temperature times the natural log of the partial pressure of the substance I divided by the P naught standard state. Now, at really low pressure, the chemical potential of the substance I in the liquid form unmixed as a function of temperature and the partial pressure I in the pure state is just going to be equal to the chemical potential of the substance I in the liquid state unmixed as a function of temperature and pressure. So then we can just say that minus RT times the natural log of the mole fraction of the substance I in the liquid form is equal to RT times this whole quantity here, the natural log of the partial pressure of the substance I unmixed minus the natural log of the standard pressure minus the natural log of the partial pressure of the I in the solution plus the natural log of P naught. So obviously these cancel out. So, and then of course these cancel out too. So we get minus the natural log of the mole fraction of I in the liquid form is equal to the natural log of the partial pressure of I unmixed divided by the partial pressure of I. So we get the natural log of the mole fraction of I in the liquid form, and that's equal to the natural log of the partial pressure of substance I divided by the partial pressure of substance I unmixed. So what we did was we multiplied it by -1 so we could flip this upside down. And then of course take e to both sides. So we get that the mole fraction of substance I in the liquid form is just equal to the partial pressure of the substance I divided by the partial pressure of the substance I in the unmixed state. And then solve for Pi, we get the partial pressure of the substance I is equal to the mole fraction of the substance I in the liquid form times the partial pressure of the substance I unmixed. This equation here is important. It's called Raoult's law. Now this is only true for ideal solutions, and it's only true at low to moderate pressures. Now what happens if we take the limit as the mole fraction of I approaches 1? Then the partial pressure of the substance I is going to be equal to the partial pressure of the substance I unmixed. Now the partial pressure of the substance I times the mole fraction of the substance I in the vapor phase times the total pressure. So remember, P is the total pressure above the ideal solution. Now the mole fraction of the substance I in the vapor phase times the pressure is equal to the mole fraction of the substance in the liquid times the pressure of the I unmixed. So here's a little diagram showing, okay, here's a container. We have the whatever mole fraction of substance I in the vapor phase, and then down here we have the mole fraction of whatever substance in the liquid phase. Now let's say we have two different components, substance A and B. We're going to form ideal solutions. So the pressure is equal to the partial pressure of substance A plus the partial pressure of substance B, which is equal to the mole fraction of substance A in the liquid form times the pressure of A when it was not mixed plus the mole fraction of B in the liquid phase times the pressure of B before it was mixed. Now we also know, of course, that the mole fraction of A in the liquid plus the mole fraction of B in the liquid has to equal 1 because we said there's only two components. There are only two components. So pressure is equal to the mole fraction of A in the liquid phase times the partial pressure of A when it was before mixed plus 1 minus the mole fraction of A in the liquid phase times the partial pressure of B unmixed. We use this to substitute in there. So rearranging a bit, we get the pressure is equal to the mole fraction of A in the liquid phase times the partial pressure of A unmixed plus the partial pressure of B unmixed minus the partial pressure of A in the liquid phase times the partial pressure of B unmixed. So we get pressure is equal to the mole fraction of A in the liquid phase plus the partial pressure of A unmixed minus the partial pressure of B unmixed plus the partial pressure of B unmixed. So the total pressure is equal to the partial pressure of A unmixed minus the partial pressure of B unmixed times the mole fraction of A in the liquid phase plus the partial pressure of B unmixed. So the reason we did that is now we have a line in the equation of y equals mx plus b. So remember, m and b are constants up here, and then x is our independent variable. So if our mole fraction of A in the liquid phase is equal to 0, then the pressure solution is just equal to the partial pressure of B in the unmixed state. Now if the mole fraction of A in the liquid phase is equal to 1, then the pressure of the solution is equal to the partial pressure of A unmixed. So here's a graph. So we have the mole fraction of A versus the mole fraction of B, and we have the total pressure of the solution. So this line here shows the partial pressure of A, and of course when it's pure we get PA star, And this line here shows the partial pressure of B. And of course, if we're pure B, it would be PB star. So this line up here is this plus this, this plus this, this plus this. It's the partial pressure of A plus the partial pressure of B. So as you can see, the partial pressure, well, in this example, we decided that PA star is greater than PB star. So the partial pressure of A is equal to the mole fraction of A in the liquid times PA star. And the partial pressure of B is the mole fraction of B in the liquid times PB star. Now, if you want to see a real-life diagram that matches this one, you could take a look at benzene and toluene. So, let's look at three functions. So, we graphed the pressure of the solution is equal to PA star minus PB star times the mole fraction of A in the liquid state plus the PB star. We also graphed PA is equal to the mole fraction of A in the liquid times PA star. And again, we have the form of y equals mx here. And then PB is equal to the mole fraction of B in the liquid state times PB star. And that too, of course, is y equals mx. Actually, more like mx, but whatever. So, let's say we have the mole fraction of A in the vapor phase times pressure equal to the mole fraction of A in the liquid phase times PA star. Then we get P is equal to PA star minus PB star times the mole fraction of A in the liquid phase plus PB star. We're going to substitute this into the above equation. So we get the mole fraction of A in the vapor phase is equal to the mole fraction of A in the liquid phase times PA star divided by PA star minus PB star times the mole fraction of A in the liquid phase plus PB star. Notice this is not the equation for a line. The only time it would be a line is if PA star happens to match PB star, because this times this would equal 0 and then you just have a constant in the denominator. Here's another graph then. So we've got the mole fraction of A in the liquid here versus mole fraction of A in the vapor phase. Now, if PA star happens to match PB star, it looks like it'll be kind of a straight line. Now, if PA star is greater than PB star, it'll bulge up this way. But if PA star is less than PB star, it'll bulge down this way. Now, if PA star is equal to PB star, then the mole fraction of A in the vapor phase is equal to the mole fraction of A in the liquid phase.